Okay, what's up guys? So today we're going to be looking at electric circuits and we're going to be discussing the rules of electric circuits. These rules are very important whenever you're trying to solve any problem in electric circuits. So we're going to start with the fundamentals of electric circuits. Those rules you need to be able to understand for you to apply them in more complex electric circuits. So we are going to discuss potential difference, current, and resistance. Okay, great. So now let's talk about the potential difference. So as you can see here in this electrical circuit, our potential difference is exactly 9 volts. We've got 3 resistors which are 5 ohm each and they are connected in series. And one thing that you should know about resistors that are connected in series is that they are actually voltage dividers. In other words, the voltage here that is supplied by the battery, which is the total voltage, is going to be divided amongst the resistors. And because in this case our resistors are of the same size, 5 ohm, then that means that the 9 volts is going to be divided equally amongst the resistors. In other words, across this our voltage is going to be 3 volts, and across here our voltage is also going to be 3 volts, and across there our voltage is going to be 3 volts. We can actually confirm this using our voltmeter here. If we connect our voltmeter here, we can actually measure the voltage. So let's do that. But before we do that, you can see the switch is open, and if we measure the potential difference across those resistors, our potential difference is going to be initially 0 because there is no current that is flowing through the circuit because it's an open circuit. Let me measure the readings. As you can see, for the first resistor on the left, our voltage is 0, no reading. And the second resistor, our reading is 0. And the third resistor, our reading is also 0. Now we are going to we're going to close our switch, and obviously we should see some changes. Right, so as you can see there, you can actually see that the current is flowing. So now let's measure and see the difference. For the first resistor, you can see our potential difference is exactly 3 volts. The second resistor, our voltage is now 3 volts, and then the third resistor, our voltage again is 3 volts, which confirmed what we just said. So in this case, we can actually conclude that resistors connected in series are voltage dividers. In other words, the voltage or the total voltage is divided amongst the resistors. And if the resistors are of the same size, then the voltage is going to be divided equally. But let's see how it's going to be like when the resistors are different sizes. So I'm going to change the 5 ohm resistors to different resistance. I'm going to increase the resistance of this one to 10 and decrease the okay, I'm going to leave this one as it is. In fact, I have to decrease this to 2.5 and do the same here, decrease it to 2.5. I just want to maintain the total resistance. Great. So what do you think is going to happen? We know that the potential difference here is the energy that is supplied to the charges that are being pushed around the circuit. And that energy is used or consumed or dissipated as the charges move through the resistor. So from my thinking, I would think that the 10 ohm resistor is going to have a greater resistance, and hence we will need more energy for the charges to be pushed through, and that would mean that we will consume or we would use more voltage to push the charges through the resistor with high resistance as compared to those resistors with low resistance. Hence, the 10 ohm resistor will have the greatest potential difference across it as compared to the 2.5, which will have less voltage across them. Okay, we can confirm this using our voltmeter. As you can see, the 10 ohm resistor have got 6 volts across it. Let's move on to the 2.5. The 2.5 ohm resistor on the middle have got 1.5, and we expect the same for the last 2.5 resistor. It also have 1.5, which means that I was right to say across the 10 ohm resistor we are going to have a bigger value, which is 6 volts, and then across the 2.5 ohm resistor we are only going to have 1.5, and the same for the other 2.5 ohm resistor, which you also have 1.5 volts. And still, as you can see, 6 plus 1.5 plus 1.5 is going to give us our total voltage. Hence, the total voltage across resistors that are connected in series will be equal to the voltage of a certain resistor, which you are going to call resistor 1, resistor 2, and resistor 3. So total voltage is equal to the voltage across resistor 1 plus the voltage across resistor 2 and the voltage across resistor 3. Now, let's move on to current. Okay, now looking at resistors that are connected in series and thinking of the current, you should know that the current that is going to pass through resistors that are connected in series is going to be the same. In other words, the current that is going to be passing through the 5 ohm is going to be the same as the current that is going to be passing through this 5 ohm and the other 5 ohm. So in other words, we are simply saying that the current that passes through all these resistors is going to be the same. It's not going to increase nor decrease depending on the resistor. Okay, so now let's check the current here. So the current, okay, so let's check the current here. As you can see, we are going to check our current using this. So if we check the total current there, our total current is exactly 0.6 amps. Let's check when it passes through the first resistor, it's still 0.6, and when it passes the second resistor, it's still 0.6, and then when it passes the third resistor, it's still 0.6. And even if we measure up there, our current is still 0.6. So you can see the current throughout this electric circuit is 0.6. It doesn't change, and hence this simply means that whenever resistors are connected in series, then in terms of the current or the current through the circuit, if there are only resistors in series, then the current through resistors in series is the same. Okay, I would like us to confirm if this is true when the resistors are of different sizes. So I'm going to change this one and make it 2, change this one and make it 2. Okay, let me change this one 2 and make it 11. Right, great. So now we want to investigate whether the current that is passing through these resistors is going to be the same too, just like when the resistors are of the same size. So let's see. We can see our current is still 0.6 because the total resistance is still the same. It's still 15, and after the current passes through the first 11 ohm, you can see the current is still 0.6, and then on the second one the current is still 0.6, and the third one the current is still 0.6. So as you can see, this simply means that the current is going to be the same when resistors are connected in series, in spite of the fact that they might have different resistance. Their current that is passing through them is going to be the same. The current that passes through the 10 ohm resistor is going to be the same as the current that passes through the 2 ohm resistor. So I can add here, even when the sizes of the resistors are different. Right, great. Now let's move on to resistance. Okay, before I move on to resistance, this means that, all right, so that simply means that the total current is equal to current through resistor 1, which is equal to current through resistor 2, and it's also equal to current through resistor 3. Great. Now let's move on to resistance. Let me quickly reset this. So I'm going to change the resistance here, back to 5. So obviously now we want to investigate what happens to the resistance if ever we add another resistor in series or we remove a resistor in series. Okay, so we can actually see what's happening here. When we've got these 5 ohm resistor, the 3 of them, let's see what happens to the current. The current, as we can see, is 0.6. And then let's see what happens if we add another resistor. So if we add another resistor here, we should remember from the Ohm's law that the resistance of the circuit is linked to the current. In other words, if the resistance increases, then the current will decrease. If the resistance decreases, then the current will increase. So here we added another resistor and let's check our current. Remember, it was 0.6 when we had 3 resistors connected in series. Now we can see our current is 4.5. This means that it decreased from 0.6. So what can we deduce from this information? We can actually deduce that if you add a resistor in series, then the total resistance of the circuit is going to increase, which will lead to a decrease in current. In other words, we are simply saying that adding a resistor in series increases the circuit resistance, leading to a decrease in current. Right there. Adding a resistor in series will lead to a decrease in the amount of current flowing through a circuit. So this is very important in your calculation. So in other words, now what we know is that the total resistance RT is going to be equal to resistance of resistor 1 plus resistance of resistor 2 plus resistance of resistor 3 plus, depending on how many you have, it just continues like that. But in this case, it's up to only 3. Right, in the next video, we're going to be looking at resistors connected in parallel. If you loved this, if you enjoyed this, please like the video and subscribe. Thank you.